This project is done by Ansar and myself, and we decided to do the project on mobile analytics on human movements. This is the first video of two. The first one is of the slide, and the second one is of the code running. So let's sort of jump into it. So the goal of the study is to predict human movements that would help reduce or even prevent injuries in the healthcare system among the handicapped, fall risk patients, and elderly. Other applications of this kind of a study is among athletes or sports, or just someone who want to keep track of their movements while they're exercising to keep good form, to improve form, as well as to prevent injuries. Some studies shows that in 2060, 30% of its total population would be over the age of 65, as opposed to where that number was only 17% back in 2010. And this huge, large jump in the percentage would have more need for that would need to be paid attention to for the senior citizens of those countries. The technology that was used for this particular study was a Samsung Galaxy X2, and the sensors that were used was an accelerometer and a gyroscope, which are MEMS, short for microelectronic mechanical systems. And an accelerometer measures the linear acceleration along any of its axes shown on the left image, and a gyroscope is on the right, where it only measures angular velocity. So some of the challenges that come with using accelerometer is gravity, because gravity has its effect on matter. Sometimes one accelerometer is not always enough to have the data that is needed. So as we could see, when a gyroscope works with an accelerometer, the data coming from the sensor is increased anywhere from 3 to 13%. Also, because of gravity, is assumed to have more effect on lower frequencies. So frequency that is less than 0.3 hertz is ignored just to clean the gravitational effects. The data that we were using is from the University of California, and this data set has 30 different volunteers within the age range of 19 to 48, and there was three categories of movements, which is static, which is sitting and standing, and laying down, which does not require any movement. Dynamic is, as the chart shows, is just walking or walking upstairs or downstairs, vice versa. And then you have complex, which would go on along the lines of standing to sitting, sitting to standing, standing to laying down, or from laying down to standing. So there was a total of 12 movements, which the study took into consideration. And in the next image, this next slide, we see a graph of someone walking versus someone going up the stairs, and the red is the acceleration in the x-axis. And you can see there's a certain pattern of acceleration going up the stairs in a particular interval, where the interval while walking isn't as symmetrical. And the subject has a sensor tied to his torso and performing other activities such as laying down, sitting down, standing. And for this study, there were 561 features which were categorized into these definitions. So you'd have the signal magnitude area. So this measures the period of activity over the three axes of time as to where the how much time was allocated in each of the axes during that activity. And then you have entropy, which basically shows how relevant a piece of information is from the frequencies that it was receiving. And the interquarter range took the difference of the Q3 and the Q1, which is the 25th and the 75% of the data, and just gave the difference of those. The auto regression coefficient is the watts per hertz. So this is a method that fits a auto regression model by minimizing the least squares, and it goes forward and backwards to predict a certain amount of errors. Um, the Pearson coefficient measures the relationship between each of the vectors in the each of the axes. So, for example, you'd have intervals of 1 on 1, which denotes positive or negative correlation, or you'd have 0, which is basically none. And this is done for the gyroscope as well as the accelerometer. Then you have the single weighted average. So this measures the average frequency of a signal S, and S again is the X, Y, and Z coordinates. Considering each of the points, it contributes in portion to its magnitude. And then you have the spectral energy or frequency band, which is a frequency version of the FTT that measures energy. And then you have the angles, the difference of the angles between each of its axes. And the next slide shows more of the formulation as far as what the feature definitions are. And there's definitely the mean and the standard deviation, the max and the min, and the skewness of the three different axes for time and acceleration, and the force of the gravity as well as the body that was being calculated as we see here. So, as I was stated before, the accelerometer and gyroscope, there were 561 data types, and we could see how the body acceleration and the gravity acceleration and the time in each of those two factors versus along the x, y, and z axes were these are the variables that were used to calculate the charts in the previous slides. So this is a quick run through of the code. Step one, basically reading the file, and if not reading the file, if not the file isn't there, returning nulls, and loading the file if the file is there for the test data as well as the training data. In step two, we basically read the features from the column and load those datas. And in step three, we have the weights which we give to the model to have more of an accurate understanding. So as far as these alphas go, 0, 0.2, 0.5, 0.8, and 1, these were all of the parameters that were inputted for the model to run. And in step 4, you have the actual model that is taking place. In line 41 is the model inputs. And GLMNet is basically a package that fits generalized linear model. And all this would be more into detail in the second part of this video. And part 5 is, again, saving the data as a SVS file. And this is a output of the model once it runs. Moving along, and this is the accuracy that was taken from the test and training data. So from the training data and the predicted data, we see that we had about almost 94% accuracy. And the idea of this data set is not to have people or patients walking around with mobile devices in a hospital setting, but this data would be used on devices either that would people wear on their wrist or their ankles or their thighs or their chest in more of as an IoT device, which would communicate with a some sort of central system in the facility. And that is basically the vision of a data set like this that we had. And this, the references, and thank you and for bearing and watching and listening. Thank you so much. Good luck.